Section 5.9, Day 1, Operations with Complex Numbers. The essential question, please write it down. How do I perform operations with complex numbers? Just as you can represent real numbers graphically as points on a number line, you can represent complex numbers in a special coordinate plane. The complex plane is a set of coordinate axes in which the horizontal axis represents the real numbers and the vertical axis represents the imaginary numbers. Remember, complex number a plus bi. This is the real part, and this is the imaginary part. The real axis corresponds to the x-axis, and the imaginary axis corresponds to the y-axis. Think of a plus bi as x plus yi. Makes sense? All right, example 1, graph each complex number. All right. So we have 2, negative 3i, which really we're going to graph as 2, negative 3, over 2, down 1, 2, 3. Right there. That is A. Negative 1 is the real part. The imaginary part is 4. Negative 1 up 1, 2, 3, 4. That's B. 4, 1, because the number in front of the I is a 1. Over 4 up 1. That is C. And, there is no real part, so that'd be 0, negative 1. And that would be D. And I'm just checking that everything looks right. Yep. So all of these real parts, well, there's 0 there, corresponds to what happens on the x-axis, and the imaginary parts go with what happens on the y-axis. And I labeled all of the points. And example 2, we're going to do in class. Recall that absolute value of a real number is its distance from 0 on the real axis, which is also a number line. Similarly, the absolute value of an imaginary number is its distance from 0 along the imaginary axis. So we're going to talk about the absolute value of a complex number. So the absolute value of a complex number, a plus bi, is the distance from the origin 0, 0, to the point AB in the complex plane, and it's denoted the absolute value of a plus bi. The reason it's an absolute value is because a distance can never be negative. So, as you can see, we're going to use this right here. To find the absolute value of a plus bi, which we're going to find in example 3, that is going to be equivalent to the square root of a squared plus b squared, basically using the distance formula. All right. So we know that a is 3 and b is 5. So find each absolute value. Recall, I'm going to scroll up a little bit. A squared plus b squared. A squared plus b squared. So we have 9 plus 25, because 3 squared is 9 and 5 squared is 25, which is the square root of 34. On this one, we have A is negative 13 and B there is 0. There is no I. So we have negative 13 squared plus 0 squared. That's 169, which is 13. And here we have A is 0 because there is no real part, and B is negative 7. So we have A squared plus B squared. 0 plus 49, square root of 49 is 7. There's our answers to all of these. And what we basically found is the absolute value, which is really a distance from 0, 0 to that particular point in the coordinate plane. Example 4, we're going to do in class. All right. Adding and subtracting complex numbers is similar to adding and subtracting variable expressions with like terms. Simply combine the real parts and combine the imaginary parts. The set of complex numbers has all the properties of the set of real numbers, so you can use the commutative, the associative, and distributive properties to simplify complex number expressions. So here's an example of what I mean. If I asked you what is 2x plus 3x, they're like terms. You would tell me that is 5x. That's exactly what we're going to do now. So in example 5, we're going to add or subtract, write the result in the form a plus bi. Okay. So right now I'm going to highlight, see, I don't want a crayon. Here's the real parts. Here's the imaginary, well, the 2 and the negative 7, but I'm going to group them together. So 4 plus negative 6 plus 2i plus negative 7i. 4 plus negative 6 is a negative 2. 2i plus a negative 7i is a negative 5i. So we get 2 minus 5i. Over here, first of all, we have to distribute that negative. So we get plus 2 plus 3i. So we have the 5 and the 2 and the negative 2i and the 3i. So 5 plus 2 is 7 plus negative 2i plus 3i is I. So notice what I'm doing. I'm adding the numbers together that don't have an I, and then I'm adding the numbers together that have an I attached to them. It's like combining like terms. Example 6, we're going to do in class. All right, let's see. Okay, so we talked about here adding or subtracting, and we did one of each. Adding, we can just drop the parentheses basically and add the real parts together and then the numbers that have the I attached to them together. But when there's a negative and we're subtracting, we have to distribute the negative. Now you can multiply complex numbers by using the distributive property and treating the imaginary parts as like terms. Simplify using the fact that I squared equals negative 1. So recall, I is equal to the square root of negative 1. We already know that. So now if I decide to square both sides, I get I squared equals, if you square the radical cancels and you get negative 1. That is important. We're going to use that. So in example 7, we're going to distribute negative 2i times 2 is negative 4i, and negative 2i times negative 4i is a positive 8i squared. You never leave I squared in your answer because we know that I squared is negative 1. And we always put it in the form a plus bi. So negative 4 minus 4i. The real part is first and the imaginary part is second. Right? So that we just distributed. We had a monomial times a binomial. Now we have to FOIL. F-O-I-L. So first is 4 times 3, which is 12. The outside is negative 3i. The inside is a positive 24i. And the last is a negative 6i squared. Combine like terms, negative 3i plus 24i is 21i. And plug in a negative 1 for I squared. So 12 plus 6 is 18. 21i. Real part plus imaginary part. 8, we're going to do in class. And here are the video questions. Please do them in your notes.